Welcome, everybody. This is our final theory lunch of the semester. And our speaker today is Rahul Ilango. He's from MIT. He's a PhD student there. And he'll be telling us about hardness or towards hardness for the minimum circuit size problem. So take it away, Rahul.
Great. Thanks for the introduction and thanks for having me here. So I'll be talking about Towards Hardness for MCSP, and it'll be about various line research papers that I've worked on in the past year, and it'll include some joint work with Bruno Loff and Igor Oliveira. And apparently Magdalene told you guys that there'd be some jokes in here, so I added in some jokes at the last minute. Well, hopefully they'll be good. Okay. So I just want to say a little bit about what the outline for this talk is going to be. So we'll start with some background. I'll tell you a little bit about MCSP, what it is, why it's interesting, what directions I think MCSP work could go in the future. Then I'll talk about these results that work towards hardness for MCSP. And finally, I'll end with some application about constant depth formulas. And if when we get to this point, like maybe you've tuned out or maybe you're not so interested in MCSP, this application isn't really about MCSP, so you can tune back in then. Okay, so let's start with some background. Here's joke one. So MCSP stands for the minimum circuit size problem, and it's a computational problem that takes two inputs. The first is the truth table of a Boolean function. So you have some fixed Boolean function, or not fixed, but it's part of your input, that maybe takes n bits as input and spits out 0, 1. And the truth table of this function is just a string that lists all the values the function takes on all of its inputs. And one thing I want to stress is that this is like a really long string. If your function took n bits as input, this is like a string of length 2 to the n. And the second input is going to be some size threshold s. It's just some integer. And the output is going to be, is there a piece of hardware, some sort of circuit, with at most s wires computing f? And to be really precise, I need to tell you exactly what model of circuits we're talking about. I'm going to come back to that later. But so this is the definition of the problem. If there's any questions about the definition, I'd be happy to answer that. Okay, cool. So I just want to give you two interpretations of this problem, kind of at a meta level. One interpretation of this problem is kind of like a circuit synthesis problem. Like, say you're Intel and you want to build some hardware chip that adds 32-bit integers or something. You might wonder, what's the smallest circuit I could get for computing that function? How small of a circuit can I build? But another interpretation that you could take for this problem is kind of as like a compression problem, where it's like you're given some sort of string, you're given some string, in this case of length 2 to the n, and you want to come up with some like piece of hardware that's like kind of represents a local compression of that string, in the sense that like if you want to know the ith bit of that string, you have some small piece of hardware where you can plug in I and get the ith bit of the string. So you can think of this either as like a circuit synthesis problem or some sort of compression problem. And so what do we know about the complexity of this problem? Hopefully it's not too hard to see that this problem's an NP. If you want to know, if you want to witness that a function has a circuit of size at most s, you can just hand over that circuit of size at most s. And because you're given this whole truth table and you're given the size threshold s in unary, you can actually go in and check, okay, does this circuit actually compute this function? What's not so easy to see is that if one-way functions exist and all this good cryptographic stuff exists, this problem can't be easy to solve. And this is something that's kind of a non-trivial connection, but if you think of this as a compression problem, maybe it might not be too hard to see. But I'm not going to talk too much about this, why this is true in this talk. If you're interested, you can ask about it. And so MCSP is some problem that's in NP, and it's probably not in P. So the most natural question to ask is the problem NP complete? And this is like a really long-standing open question. It goes all the way back to Levin when he published his version of the Cook-Levin theorem. He was hoping to show that MCSP was NP complete. And in some sense, it goes back even further than that, to the 1950s. But, yeah. Okay. Any questions about MCSP and what we know about it? Cool. So I've told you what MCSP is, but I haven't told you why we care about MCSP. And so generally, the reason why you might care about some specific problem like SAT is that answers to questions about the complexity of SAT led to interesting developments in complexity theory, things like the PCP theorem, things like practically useful SAT solvers. And so that makes the following claim pretty bold. MCSP is more fundamental than SAT. And like, what daring research would dare make such a blasphemous claim? My name is Rahul, but this isn't me, Rahul. This is Rahul Santanam. So if you have any pitchforks, you can direct it at him. But you're probably asking, why are all these Rahuls interested in MCSP? And I'm glad you asked. It's primarily the connections the problem has. It has connections to these other areas of theory that are pretty interesting. So there's these connections to cryptography, to learning theory, average case complexity. And I don't really have that much time to talk about all these connections, but I do have bonus slides on them if you want to ask about it at the end. But I will highlight one connection that is kind of in vogue right now and I think is pretty interesting. And that's some connection to cryptography. In particular, people are trying to prove the following lines of implications. They want to show that if MCSP is hard in the worst case, then it's hard in the average case. And if it's hard in the average case, one-way functions exist. So this is some line of work that's trying to put the foundations of cryptography on kind of solid complexity theoretic grounds, saying that if MCSP is hard in the worst case, and ideally if it was NP hard, we would have something like P not equal to NP, which implies that one-way functions exist. And in fact, we know that if one-way functions exist, then MCSP must be hard in the worst case. So this would all be in equivalences here. And what's neat about this line of work is that, like, in the past 2.5 years, there's been some significant progress on this. So 2018 at Fox, Hirahara had this paper that showed a version of MCSP is hard in the worst case implies MCSP is hard in average. And so this was like a pretty cool work. It won Best Student Paper. And this year at Fox, Liu and Pass had this amazing result which showed some version of this thing. Not quite for MCSP, but some like Turing machine version of MCSP. And so there are some like technical details. You can't compose this thing with this thing yet. This works with a different case of average case hardness than this result. And they're for like slightly different problems. But I think over the next few years, this is like a really exciting line of work. And if you're interested about what these theorem statements are, I can talk more about them. Yeah. Cool. All right. So now I've told you what MCSP is. I've told you why people kind of care about MCSP. But now I want to come back to this question of, is MCSP NP hard? And so I already mentioned this is kind of a long-standing open question that like goes all the way back to Levin and in some sense even earlier than that. But why is this like a very difficult problem to understand? I mean, we have like thousands of problems which we know their complexity of. Why is showing MCSP NP hard so difficult? Well, kind of the intuition researchers have on this is that if you look at what the difficult no instances of MCSP correspond to, well, it's a truth table that kind of requires large circuits. So you have some truth table, and in order for it to be a difficult no instance, it means that it in some sense requires large circuits. And finding functions that require large circuits, that's like something we don't really understand very well. We don't know how to produce functions that require large circuits, at least deterministically. And so that kind of hints that like it might be difficult to get a reduction to work. Like if you can't even produce hard instances of the problem, what hope are you going to have to produce a reduction? And in fact, this can be formalized. So there's some theorems by Kapaneth Tsai and Murray and Williams and others that I haven't mentioned here that say that getting like a deterministic polynomial time reduction, that's something that would probably require a breakthrough. So what does that mean? Does that mean that like maybe understanding whether MCSP is NP hard might be like a very difficult question that we should like put to the side and come back to later? Is this something that we're like ready to attack right now? I actually think so, or think that we can attack it, but maybe not in this lens. In particular, there's kind of like two holes here that I think we might be able to exploit. In particular, like this is talking about deterministic reductions. What about randomized reductions? So while we might not know how to come up with functions requiring large circuits deterministically, if you were allowed to use randomness, then all of a sudden it becomes very easy to come up with functions that require large circuits. You just pick one at random, and then by a counting argument, that function requires large circuits. So it's not clear what barrier there might be to showing that MCSP is NP hard using a randomized reduction.
So a quick question, Rahul.
Yeah.
So I guess the reductions can run in time poly in 2 to the n, right? So I guess the difficulty here is that even in some class like E or X, like we cannot produce a truth table in exponential time, which requires, say, n cube circuits. So
yeah. So I believe that in exponential time, the best you can do is come up with a truth table that requires 3n or 5n size circuits, depending on what basis you're in. So we don't even have like super linear lower bounds, even when you talk about x and maybe even x to the np.
Right. So, yeah, I was just going to ask that too, because you might be interested in sub-exponential type reductions, right? So you might even
great question.
Yourself, yeah.
And that's what I'll get to next. So like one hole here is the deterministic thing, and very good, like pointing out what if you're allowed to use sub-exponential time reductions. And
I have another question. Sorry, before we go on.
Sure.
I don't see why we need functions requiring like particularly large circuits. Like you had the S as part of the input. So at no instance might just be, okay, this requires n+1 size circuit rather than n size circuit. That would already be potentially a difficult no instance, unless I'm missing something.
Yeah, so that is true. That could be like a potentially difficult no instance, but like how difficult? So like since you're given this whole truth table of length 2 to the n, if you were going to brute force over all circuits of size n+1, that ends up being something like 2 to the n log n. So you wouldn't get the hardness you would get from that would be kind of in like the low regime. But if your assumption is something like ETH, then you might be able to still get MCSP not in P based on n versus n+1.
Okay.
So that, yeah, very good. And I guess this connects both of your questions. So like if you're talking about sub-exponential time reductions, not only do I conjecture that this statement is true, I think it's almost definitely true, but I think it might even be provable. So I've thought a lot about this, and I don't see like an immediate barrier that comes to proving that, say, the exponential time hypothesis implies that MCSP is not in P. And I think even using like linear size lower bounds or n versus n+1 lower bounds, you might hope that you can prove this kind of statement. Okay, and these two things, randomized reductions and exponential or sub-exponential time reductions, they're things that I'm going to come back to in the results section. Cool. Any other questions about this? These are good questions. Cool. Oh, this is a slide that I just added in the past 5 minutes based on Magdalene's thing. So MCSP plus Rahul equals a destroyer of worlds. So this is my personal dramatization. So way back in the late 1990s, Impagliazzo came up with these kind of 5 worlds of complexity that we might be living in based on what we know about crypto and based on what we know about complexity theory. So he came with his telescope and he kind of plotted out these 5 worlds, which is algorithmica, heuristica, a bunch of different worlds, which correspond to things like maybe NP is like easy to solve in the worst case, maybe it's easy to solve on average, but hard in the worst case. Maybe it's hard, but you don't get crypto, and like various versions of this. And so kind of a perspective some researchers have, in particular, not me, Rahul, but the other Rahul, is that you can use MCSP to kind of destroy these worlds. So I think this is like kind of a perspective that some researchers have on this. In particular, kind of like this worst case to average case reduction that Hirahara has, he talks about it as trying to eliminate kind of this middle world heuristica. And there's another paper that Rahul has that is trying to take aim at Pessi land. So the hope is that by understanding MCSP, maybe you might be able to eliminate some of these worlds. That's kind of like an overarching goal. It's something that like I think it might be far away. I don't know. It's debatable how far away it is. But if you're interested, you can ask me about it, and I can talk a little bit more about that. And so the final thing that I want to talk about, and this will connect more to our results later on, is another motivation for why one might want to study MCSP, and that's to prove like kind of new looking circuit lower bounds. And this is what I mean by that. So if you look at the circuit lower bounds right now that we know how to prove, the few that we know how to prove, they kind of prove circuit lower bounds that are in some sense easy to recognize. And what do I mean by that? I mean that like when you look at the truth table of the function, you're kind of able to tell, oh, okay, this is a function for which the circuit lower bound applies to, and okay, that's going to be a hard function. So for example, if you're familiar with like random restrictions, you can kind of like look at the truth table of functions, say, okay, does this simplify under random restrictions or not? And if it doesn't, maybe it's a hard function, something like that. And this is very closely related, but not exactly the same as this natural proof barrier that Rasburov and Rudich have. So there's some barrier against proving circuit lower bounds that somehow involves circuit lower bounds that are being easy to recognize. And the relevance of this to MCSP is as follows. You can kind of break up the instances of MCSP into like 4 different categories, like the difficult no instances, kind of the easy no instances, the easy yes instances, and the difficult yes instances. So what do it's kind of fuzzy what the meaning of like easy and difficult is here, but you can be like, there are some instances of like SAT, for example, that it's like very easy to tell that these are actually no instances of SAT, or very easy to tell that they're like yes instances of SAT. And similarly, there should be, it should be like kind of similarly the case for MCSP. And so what does it mean that many techniques that we have prove circuit lower bounds that are easy to recognize? It means that basically all the circuit lower bounds we know kind of fall into this category, where they're kind of like easy no instances of MCSP. And the relevance of that to proving hardness for MCSP is as follows. Like, if you're going to give a reduction from, say, SAT to MCSP, or some other hard problem to MCSP, you kind of want to make use of the difficult no instances and the difficult yes instances. Like, if you have a reduction that only maps into the easy no instances and the easy yes instances, then not only do you have a reduction, but you have an algorithm. And because of that, like, what it suggests is that if you're going to give a hardness reduction to MCSP, you're kind of going to have to use lower bound techniques that maybe kind of fall outside of like the category of our usual types of lower bounds, because or lower bound techniques, because you're probably going to need to identify no instances in this category. So you're probably going to have to prove lower bounds that maybe don't look like existing type of lower bounds. And so this is like a pretty abstract argument right now. And I'm going to come back to this in the application at the end, where I'm going to try and argue, okay, here was a reduction that involved MCSP, and it kind of produced a lower bound that was maybe of a different flavor than the usual type of lower bounds that we have. So this is like my last background slide. Now, next I'm going to go into the results, but if there's any questions about what I've talked about so far, I would be happy to answer them. Great. All right. So now it brings us to the results. So I'm just going to give a quick overview of the results before I get into them in detail. So in this section, I'm going to talk about hardness for like various versions of MCSP, and that's what this talk is kind of about. In particular, I'm going to talk about like 4 different versions, and I think if this is maybe your first introduction to MCSP, it's going to be kind of hard to like wrap your head and contextualize each of these 4 versions. So what I'd like to emphasize more is like what the takeaways from these results are. In particular, these takeaways are going to be kind of related to things that I've talked about previously in the background, like how sure are we going to, like, what kind of evidence can we construe of this suggesting that MCSP itself, like instead of just this version of MCSP, like maybe learning that all 4 of these versions of MCSP are hard suggests that the original problem should be hard. What is the power of randomness in a reduction? This different type, how do these reductions imply different type of circuit lower bounds? And what is the power of the exponential time hypothesis in getting these reductions? So these are kind of the takeaways that I'm going to emphasize more in the next few slides. Okay, so chronologically, the first result was about this modified version of MCSP that kind of got to use oracles. So in usual MCSP, you get like this truth table of a Boolean function f and a size threshold. That's still there. But now, in addition, you'll also get the truth table of an oracle Boolean function. So you get a fixed Boolean function as input. It's not a language, it's a function. And now the output is going to be like if you're given a gate that computed this oracle function for almost free, how hard is it to compute this function f? So does there exist a circuit with O oracle gates and at most S wires computing f? So you can think of this as like I've just expanded your gate set by adding in an extra function O. And what's kind of interesting about this problem is that you can kind of prove that if you're going to use deterministic deterministic polytime many one reductions, proving it's NP hard requires a breakthrough. So it would require separating two complexity classes that we think are very different, but we don't know how to separate yet. But kind of interestingly, if you use randomized reductions, I was able to prove that this problem is in fact NP hard. And so this is kind of a demonstration of like the power of randomness in proving hardness for MCSP type problems. And what's kind of interesting is that like this proof is like not too hard. I mean, I don't have time to go into it now, but really the innovation was like looking at this problem definition. And in terms of the takeaway, I think before this result, people were talking about, okay, we don't know how powerful randomness is. Maybe you can make use of randomness in these type of reductions, but we didn't have like a proof of concept. So I think this result really gave that proof of concept of, okay, here we were actually able to use randomness. Okay, so that was the first result. And then the next result that came out was looking at MCSP for multi-output functions, which I think is like a pretty natural version of MCSP. So here, again, you're given a size threshold S, same as before, but now you're given the truth table of some function that takes in n bits and spits out multiple bits. So it spits out n bits. And the output is like, can you come up with a multi-output circuit that computes this function with size at most S? And yeah. And so we were actually able to show that this problem is also NP hard using randomized reductions. Again, I don't have too much time to talk about the techniques, but the way that this result was proved was like building off of the previous result for Oracle MCSP. And again, the takeaway from this result was, okay, here's another proof of concept that randomness is useful for maybe a problem that looks closer to the original MCSP problem. Okay. And then the third problem, or the thing that came next, was a version of MCSP for a restricted class of circuits. So MCSP is a circuit minimization problem. You could imagine like you might care about the circuit minimization problem over different classes of circuits. So in this case, we were talking about depth D formulas. So what does that mean? You're still going to get the truth table of a Boolean function. You're still going to get a size threshold. But now the output is going to be, does there exist a depth D formula with at most S leaves computing F? And this is kind of a very natural problem because it's like, maybe you're Intel and you want to build like a highly parallelized circuit for computing some function. And you want to know how hard is that to do. And so NP hardness was already known for the D equals 2 case of this. So it was already known that for DNFs, this problem was NP hard. And this is something that's kind of counterintuitive because you would think, okay, we know DNF MCSP is NP hard. Like the general version of MCSP should only be harder than the DNF version of MCSP, right? Like general circuits seem much more complicated than DNFs. Surely if DNF MCSP is NP hard, then like regular MCSP is NP hard and the D equals 3, 4, 5 case of depth D formula MCSP should be NP hard, but that's something we don't know how to do, which is kind of intriguing. But yeah. So NP hardness was known way back in the 70s for the depth 2 case. And I guess 2 years ago, this was extended to like DNF of XOR formulas. But in our result, what we show is that the depth, if for every fixed constant D, this problem is NP hard under randomized quasi-polynomial time turn reductions. So in terms of takeaways here, So the key ideas behind proving this was one, to work by induction on D. I think it's a fairly natural strategy. So the D equals 2 case was kind of already known. And our inductive step had this kind of interesting interesting technique where we were able to kind of lift depth D lower bounds to depth D+1 lower bounds. And this is I'm gonna come back to this because it's gonna be the application that I'm gonna talk about at the end. But the takeaways from this theorem was, again, that randomness was useful. What's interesting about this result compared to the previous two results, where in the previous two results, we were using randomness to sample kind of uniformly random functions. Here, we actually don't sample uniformly random functions. We sample functions that have properties that are like random functions provably do not have. So it's kind of a more subtle use of randomness. And I think it's a more powerful proof of concept. But maybe the more interesting takeaway here is that this technique, which I'll talk about more at the end, I think is a good example of how proving lower bounds for MCSP or proving hardness results for MCSP might reveal different types of lower bounds. And I'm going to come back to that at the end. Okay. Cool. There's a couple, there's a lot I covered on the slide. So if there's any questions about this or the previous two slides before I get into the last result, happy to take any questions.
I had a question.
Yeah.
How should I think of the complexity class of problems that are NP hard under randomized reductions? Like, it clearly includes everything NP hard and then something a bit bigger than that, but like, how much bigger, I guess?
So there are, besides the ones that I've talked about on the slide or these slides, there are other problems where we only know that we only know how to prove that they're NP hard using randomized reductions. And like, despite, I think there's some work by one of the Vaziranis, like back in the 80s that did something like this. So I think people have not shown that like these two classes of problems are two classes of problems are like the same. I think you should think of it as like a little bit bigger slice. I don't think it's that much bigger. I mean, it's hard to quantify what bigger is here, but I mean, another way you could frame this is like, this problem is not in P as long as NP is not equal to BPP or something. Or I guess in this case, there's quasi-polynomial time. So it's like, this problem is not in quasi-polynomial time unless NP is equal to BQP. Is that true? Actually, it might be more subtle than that. Okay, I'm not. Maybe I'll come back.
But there might be that kind of a result, as in if some class that's only a little bigger than P isn't the same as NP, then
yeah.
Okay, gotcha.
Also, there should be like standard complexity theory hypotheses under which these problems are just NP hard, right? De-randomization based hypotheses.
Yeah, that's what I was wondering. Is it necessarily the case that if like P equals BPP, then like any problem that's NP hard under randomized reductions, does that imply it's NP hard under deterministic reductions? And I actually think there might be some subtlety there.
I'm thinking of something like, if like X does not have, sub-exponential size SAT gate circuits, then.
Oh, okay.
Then maybe like these things that are randomized reducible are also polynomial time reducible. Maybe something like that.
Yeah, that seems plausible. I think that would be at least for the results I mentioned earlier. I think that hypothesis would imply a deterministic reduction.
Yeah.
Okay, great, thanks.
Yeah, any other questions?
Yeah, so just like to understand, like, what are you using randomness to extract exactly? Like hard instances? Is it like easy for you to describe like what, like maybe in the first few examples that you gave, like how exactly you used randomness?
So in the previous two results, we used randomness just to sample, a uniformly random function, and we use the fact that that uniformly random function is going to require large circuits. And in fact, not just large regular circuits, but even like large circuits when you look at an even more powerful circuit class. So in the first two results, we're basically just using it to get hard functions. In this case, things are actually a little bit more subtle. We're using randomness to sample functions that are computable by DNFs, that are almost optimally computable by DNFs, if that made sense. So if you sample a uniformly random function, you can figure, Lupinov showed in the 60s that you can find a depth 3 formula for that. That's like basically optimal. But if you try and get a depth 2 formula for that, that's basically optimal. That's like actually false. Like for a uniformly random function, it's much easier to compute it at depth 3 than it is to compute it at depth 2. So in this result, we actually had to, because we're kind of like lifting from the depth 2 case, we needed to find functions that are easily or pretty much optimally computed by DNFs. And because of that, the use of randomness had to be a little bit more subtle. And in fact, the way that we get those functions is very nice. What we do is we just look at Lupanov's optimal depth 3 or nearly optimal depth 3 construction, and we look at like the depth 2 subformulas in that. And because like the depth 3 formula needs to be optimal or roughly optimal, the depth 2 parts of it also need to be basically optimal, which I think was like a cute argument.
Okay, thanks.
Great. Any more questions? Cool. And so that brings us to the last result, which is about MCSP for partial functions. So what if your input truth table, instead of being a total function, was a partial function, a function from 0, 1 to n to maybe 0, 1 star. And so you still get a size threshold s, and now the output is, oh, sorry. And I want to stress here that like f is a partial function, but I'm still giving you this full truth table of length 2 to the n here. Like there's various representations you might think of for partial functions, but it's important that I'm like using them like the most explicit one. You don't get like a more succinct input or something, which might make the problem easier or might make the problem harder. And now the output is, can you compute this function with a circuit and or not fan into, the usual type of circuits, with at most s wires where you only care about the inputs on which the function is defined. And kind of interestingly, this has been historically an important intermediate problem. So like I mentioned that this DNF version of MCSP was NP hard, and like DNF XOR version of MCSP was NP hard. Like they were both proved by first showing this partial function version of the problem is NP hard, and then reducing the partial function version to the total version. So historically, this has been a kind of an important intermediate problem. And so we were able to show that this problem is like not in P under ETH. So it's kind of like a first step or the takeaway. Oh, maybe I should put the takeaway before the ideas, but the takeaway here is like, this is like a proof of concept with ETH being useful. And I think even on its own, it's kind of an interesting result. And the way that it's proved is actually kind of like exactly what Isaac said. We're able to distinguish kind of like that. We show that distinguishing the n-1 case from the case where a function has circuits of size n, which is kind of like the most basic thing you could do. We show that that's something that basically requires brute force to do. That's how we're able to show that this problem is like not in P under ETH. And kind of the key ideas for proving this was some sort of twist on gate elimination. And we worked from this problem. It sounds like a really long problem, 2n by 2n bi-type permutation independent set, but it's actually not so nasty of a problem. And it was known that like this problem couldn't be solved faster than brute force under ETH, and we were able to reduce this problem to partial function MCSP. Okay, cool. So let me just wrap up the results section by kind of recapping what the takeaways were. So one, I think the research gives strong evidence that randomness should be useful, or at least we have several proof of concepts now that randomness is useful for showing hardness for MCSP. We have one example of using ETH to show hardness for like an important version of MCSP. I didn't really talk about this that much, getting different types of circuit lower bounds from hardness results on MCSP, because I'm going to talk about it more in the application section. And hopefully, like showing that these 4 versions of MCSP is hard kind of gives you evidence, or kind of implicitly suggests that maybe the original version should be hard. And I think some people like Eric Allender, who was kind of my undergrad advisor, was kind of on the fence about whether MCSP should be NP hard. And I think some of these results helped convince people that like maybe we should expect that this problem is NP hard or something like that. And I think the biggest open question from those line of works is this question: is MCSP not NP under ETH? And if you look at the paper, I actually kind of suggest a line of attack on this. I'm not sure how to do it yet, but I feel like we don't need that many more new techniques in order to solve this. We'll need a new technique, but it's not going to be a technique that'll require separating X from ZPP or anything like that. So I think it's an interesting question. Okay, Any questions about the results or these takeaways?
It's not about these results or the takeaways, but is there like an ETH for MCSP, and is it useful for something? Like you assume it can't be done in like better than whatever S to the S 2 to the N time?
That is a great question. And in fact, it's a really long-standing open question because so when MCSP was first studied, it was first studied in the 1950s in the Soviet Union. And what they were interested in were questions that required paraboric, which in Russian, I'm told, translate to brute force search. So they were wondering, okay, what computational problems? They had like read Shannon's work on circuits and they read Turing's work on computation. And they were like, okay, what problem can we come up with that you like can't do better than brute force on? And MCSP was their conjecture. They were like, oh, I don't think you can do better than just brute forcing over the S to the S solution for MCSP. So these are called like the paraboric conjectures. So it's a long-standing open question with a lot of history to it. I think, and this recent paper by Liu and Paz on like one-way functions and Kolmogorov complexity, I had asked them a question related to this. I was like, okay, if you assume for their version of MCSP that you can't do better than brute force, what conclusion do you get? And they think that you should be able to get like, if you can't do much better than brute force on a version of MCSP, then exponentially strong one-way functions exist or something like that. So like, yeah, I mean, I'm not totally sure if they like went through and did the work or like checked everything, but there's the possibility that how well you're able to beat brute force on MCSP is related to how strong of crypto we can get.
Great, thanks.
Any other questions?
Are there any approximation versions of MCSP known?
Yeah, so that's a good question. As far as we know, or we have cryptographic hardness for like basically any reasonable approximation of MCSP. Like if you want to distinguish, like even with like what's the best way? I haven't really introduced the parameter. Okay, I'll say it like this. Basically, any approximation that might be interesting to MCSP is cryptographically hard for general circuits. Actually, it's interesting in like the constant depth circuit case. This is not really understood so well. How hard should these things be to approximate? But in the general circuits case, like approximation should be pretty hard.
So even like S versus poly S?
Yeah, and in fact, yeah, S versus poly S is cryptographically hard.
Cool, thanks.
Well, when S is large enough. I mean, if S is small, then
right.
Yeah.
This is probably a really dumb question, but like, does search to decision hold for MCSP?
That's a great question. And in fact, it was another question that I think that goes back to the 50s, where people were like, okay, is the search problem hard? Is the decision problem hard? And it's not known. It's been kind of like a long-standing question. What is interesting is that there has been like these slight progress, like partial search decision reductions have been known, were just recently proved by Carmesino and Pagliazzo, Cabinets, Kolokolova, or I guess this isn't that recent, it's like 2016. But what's cool about those results is that these like barely non-trivial search decision reductions that they proved actually had like big implications. They ended up being a very important ingredient in Hirahara's worst case to average case reduction. So I think, so we don't know a lot about search decision reductions, but it seems kind of interesting in that like historically they've played kind of, they've been important ingredients and cool results. So maybe understanding that question better is interesting.
Thanks.
Great. These are great questions. Okay, so, Venkat, do you have a question?
Yeah, I was just wondering, are there any fast exponential algorithms for MCSP? In the spirit of Ryan's question, like, I mean, could you conjecture like a set analog for MCSP, or would that be too?
No, I think it's, well, if you ask me, I think it's probably true. And Ryan has spent a decent amount of time thinking about, for the formula version of MCSP, the minimum formula size problem, can you beat brute force? And he hasn't been able to do it. Yeah, if I had to guess, I would say that the Seth version of the Seth for MCSP should be true. And as I mentioned earlier, this is probably related to how good of crypto you can get. Yeah.
Yep. Thanks.
Okay, cool. So now let me move on to this application. And so if you tuned out by this point, or maybe you're not so interested in MCSP, like you don't have to know anything that I mentioned earlier in order to understand this part. So you can feel free to tune back in. So it's going to be about large gaps in formula complexity between depths. So let me just remind you guys of the model of constant depth formulas. So constant depth formula, you have like an underlying rooted tree of constant depth, and at each internal node in the tree, you get to use an AND gate or an OR gate, and we can assume all the NOT gates are kind of pushed to the bottom. And let me introduce some notation. I'll say L sub D of F is going to be kind of like the depth D formula complexity of F, which is the minimum number of leaves in a depth D formula computing F. Okay, cool. And so the question that we addressed was kind of what is the power of extra depth additively? That is, how large can you make, if you have a function f, how large can this quantity be? The depth d complexity of f minus the depth d plus 1 complexity of f. And just a reminder of what that notation was. So if you look at like the d equals 2 case, it's very easy to prove that this thing must be large. If you take parity, computing it at a depth 2 basically requires n times 2 to the n, like the worst possible thing. And if you want to compute it at depth 3, then you can use divide and conquer to get something like 2 to the square root n. So you can show that there's a large gap between 2 and 3, and in fact, there's even better functions than parity. But what about higher depths? As far as I know, the best result for higher depths comes from these depth hierarchy theorems of Hastad. And he showed that there exists a function f such that the difference between depth d complexity and the depth d plus 1 complexity is like 2 to the n to the 1 over d, roughly. And in fact, he proved something much stronger. He proved that like there exist functions such that this quantity is exponential and this quantity is like linear. So it's like much stronger than an additive separation by itself. Yeah, so this is the best thing I think was known. And as far as I know, it's not even clear how you can do better exponentially. Like if I let you, it's not even clear how to do better existentially. If I allowed you to like pick a function at random or do something like that, it's not even clear that you can do as good as this, because basically once you get past d equals 3, these two quantities are basically the same for random functions. And the intuition there is like best way to compute a random function is a lookup table. Lookup tables don't require too much depth. And so what we show is that there actually exist functions such that this quantity is pretty large. So we improve the dependence on d here significantly, as large as 2 to the omega sub d of n. And so there's some caveats here. One, our proof is existential. Roughly, our function f is going to be some mix of a random function and parity. Two, I only know how to prove it for formulas. I suspect it's true for circuits, but I don't know how to prove it. And finally, our proof only shows that there exist functions with like an additive gap here. Like if you look at the proof, the functions that we prove this theorem for have kind of like a constant factor difference there. So multiplicatively, there's not much of a gap, even though additively there is a large gap. So any questions about the setup? Okay, cool. So let me talk a little bit about why this is interesting and how it's proved. So I've just restated the theorem here. It's exactly what I said on the previous slide. So one thing that's interesting about this is it gives pretty good parameters. Like if you're going to try and prove this using things like the switching lemma, it's not clear to get how to get a dependence on D that's this good. But I think what's more interesting about this lower bound is that I want to come back to this thing that I mentioned previously about different flavors of lower bounds. So this lower bound came about by trying to prove a hardness result for MCSP. And one question you could ask is how well does this lower bound fit into, say, the natural proofs barrier against proving circuit lower bounds? And if you look at this, if you're not familiar with the natural proofs barrier, it's not a big deal. But basically, there's like two conditions a proof needs to satisfy, a circuit lower bound needs to satisfy in order to naturalize. And one is that it kind of has to apply to big class of functions. And our lower bound seems to apply to a very specific class of functions. It seems to apply to functions. It'll become clear on the next slide when I kind of tell you what this function f is, but it seems to apply to a very specific class of functions. And it's not even clear if random functions satisfy the lower bound that we prove. So like it's not even clear whether you could hope that a large number of functions fit into our lower bound. And the other thing is that our technique is not very constructive and doesn't seem to be very what's called p-poly constructive in the natural proofs framework, because actually the way that we lower bound things is we lower bound the complexity of a function in terms of quantities that are kind of NP hard to compute. So it's not clear how to make this like a very constructive argument. And we also use randomness. So. And the last thing I want to mention about this lower bound is a lot of the lower bounds we know against constant depth circuits and formulas kind of work bottom up. This lower bound works top down. So, okay. So now let me tell you how this strategy is proved, or how this theorem is proved. So it's proved by induction on D. So in the for the D equals 2 case, we just use the parity function. And now for the D greater than or equal to 3 case, what we do is, assuming we have some function f that has a gap between depth d and d plus 1, we kind of lift that gap by creating a new function h, such that that new function h has a d plus 1 versus d plus 2 gap. And what I'm going to talk about for my remaining time, looks like I have about 8 minutes, is how you construct this function h, or roughly how you construct this function h. Okay, any questions up to this point, maybe about the theorem statement or how it's proved or why it's interesting? Okay, cool. So let me tell you about what the idea here is. So our goal is to lift gaps to larger depths. So kind of by what we do is we start with this function f, which has a d versus d plus 1 gap. And we want to come up with a new function h, which has a large gap for d plus 1 versus d plus 2. So what do? So it turns out via some like De Morgan law-ish tricks plus some direct sum-ish tricks that I'm going to kind of gloss over, that we'll only need to prove a lower bound, or we only need to show that there is some function that's easily computable at depth d plus 2, but is not easy to compute at depth d plus 1 with an OR gate on top. So we can assume that all the formulas we want to lower bound against have an OR gate on top. And this is going to seem kind of crucial to our definition of the function h. So what we're going to do to construct h, in fact, this is not exactly what you want to do, but it's kind of easier to say what this is, and I'll come back to what exactly the exact construction is. So we'll pick a function g uniformly at random on 2n input bits. So f is a function on n input bits, and g is a uniformly random function on 2n input bits. So this is kind of g is some function that's like much, much harder to compute than f could possibly be. And then our function h is just going to be the and of f and g on distinct inputs. So you have these inputs x that'll feed into f, and then you and that with the inputs y that feed into g. And kind of the intuition here is like, okay, if I'm only allowed to compute this function h with an OR gate on top, well, h is a function that you kind of want to compute with an AND gate on top. And so you might think, oh, if I only have an OR gate on top, that top layer of depth is kind of useless, and I'll have to kind of skip that layer of depth and go to one depth lower. And that's why we're able to like kind of lift depth d to d plus 1, because like you have an OR gate on top, but that's not so useful for computing h because you kind of want to do it with an AND. And so now let me state what the formal theorem for the lower bound is. So I'll introduce some notation. So I'll say L or d plus 1 of f is kind of the depth d plus 1 complexity of f when you consider formulas with only an OR gate on top. So it's the minimum number of leaves in any OR top depth d plus 1 formula for f. And what our theorem is that with high probability over the choice of g, the depth d plus 1 complexity of this h function is lower bounded by some quantity involving the depth d complexity of f. So there's like a lot of notation here. So, but kind of like the high level takeaway is that like there's some function h whose d+1 complexity is lower bounded by a quantity involving the depth d complexity of f. And if, just to give you some context for what this lower bound is, it turns out like the naive lower bound here is that this quantity is lower bounded by like the depth d+1 complexity of f and the depth d+1 complexity of g. This is something that's like not too hard to prove, but maybe if you haven't seen it before, I'll just gloss over it. So really the power of our lower bound is that we're kind of able to trade the lower bound on f from being about depth d complexity, or d+1 complexity to depth d complexity. And if you're interested about how tight this lower bound is, so a really trivial upper bound on h is, so if you, let's say you wanted to compute h and forgot about like the top layer of depth, like you have an OR gate on top, let's like not use that. Let me just use everything below that. One way you could compute h is compute a depth d formula for f with an AND gate on top, and AND that with a depth d formula for g with an AND gate on top. If again, there's a lot of notations that might have been kind of hard to follow, but this is like not a too hard upper bound. There's nothing tricky going on here. So if you look at how tight these lower and upper bounds are, well, the first terms are the same. So really any slack you get is coming from these two terms. And so the slack you get is like, what's the difference between how much easier is it to compute g at depth d+1 than it is to compute g at depth d? And if you choose this function g appropriately, it turns out you don't want to choose it uniformly at random, but by some other approach that I actually kind of mentioned earlier, you can make sure that this quantity is not too big. So then this lower bound ends up being pretty tight. Yeah. So any questions about the theorem statement or the definition of this h function? Or maybe even some of the intuition behind it?
So to clarify, this is sort of one side of the bound, and then we're going to need to say that with d+2 you can compute it easily. And I guess you're going to say that that's going to be inherited from being able to compute f easily at d+1. But I guess what I'm missing is, why isn't that formula dominated from needing to compute g at depth d+1?
Yeah, that's a good question. Basically, what we're going to do is when you make your choice of g, you're going to have to balance. You want to make sure that the complexity of g is like not too much bigger than the complexity of f. So yeah, so there'll be some. You don't want to actually choose g completely at random. You want to choose it so that it's like more complex than f, but not too much more complex than f, and such that this lower bound and upper bound are kind of close to each other.
Okay.
Does that make sense?
Yeah, that makes sense.
Any other questions? Okay. So I guess it is 1 o'clock. So I don't know. I guess I have like one more slide here, but I don't know, Magdalene, maybe is it better for me to just like go to the end my question slide, or?
I think if it's just one slide, it's probably fine.
Okay. So yeah, maybe instead of doing this slide, I'll do one of the bonus slides, which I think might be more useful. So I just want to tell you like roughly how this lower bound works. I'm not going to tell you like why things are true, but I just want to tell you the mechanics of how the lower bound works. And it's a proof by contradiction. So you say you have some formula that computes h and beats the lower bound. What you do is you take this formula phi, and I'm gonna transform it into something that's gonna try and compute this really hard function g at a low cost. So that's kind of like the paradigm for the proof. If you come up with a formula that computes h that's like very cost effective, you can translate that into a formula for computing g that's very cost effective. And because of that, that's how we get our contradiction. And the way that you transform this formula phi for h into a formula for g is kind of very simple. You take the formula, so this is going to be like a depth d+1 formula for computing h, and you just kind of split it in half at random. So for each one of these subformulas that you put into it, you're going to like kind of put them to the left side or the right side, and then you look at the two formulas that you'll get some formula on the left and you'll get some formula on the right. And then we actually argue that both of these formulas compute a strong approximation to G, in particular, a strong non-deterministic approximation of G, but these formulas are each kind of small. And that's roughly how the contradiction works. So you take some formula that beats the lower bound, you split it in half at random, you look at the left side, look at the right side, both of them are computing G to an extent, and you get some contradiction. Okay, so let me go to my question slide. If you're interested about more of the connections on MCSP, I have a bonus slide on that. I think the most interesting open questions are, can you prove MCSP is not NP under ETH? Can you prove an analog of my results for constant depth circuits? I only know how to prove them for constant depth formulas. And can you improve this gap theorem that I mentioned here?
All right. Let's thank our speaker. While other people are maybe thinking of questions, this isn't super directly connected, but something I was wondering about MCSP in general. There's been a lot of recent work on indistinguishability obfuscation, making it a lot more practical. And it feels, I don't know, maybe this is a weird feeling, but it feels related to minimum circuit size in that you're trying to say things over like for all circuits that compute this function sort of questions. Are there connections to that in here?
Yeah, that's a great question. I think so. I think there'll be two parts to my answer. Right now, I think a couple of researchers, including the other Rahul, are thinking about, can you base indistinguishability obfuscation off of MCSP? Like I mentioned earlier in the talk that some people are trying to base one-way functions off of MCSP, but maybe you could even go like further than that. Like you could base indistinguishability obfuscation off of MCSP. So some people are thinking about that. On the other hand, for a concrete result, there's actually a result that, let me see if Russell and Pagliazzo and some other people were working on that basically showed that if you had indistinguishability obfuscation, you might actually be able to prove that MCSP is NP hard. I think there's some result, like if indistinguishability obfuscation exists, then NP is contained in BPP if and only if MCSP is in BPP or something like that. So this is kind of like almost a hardness result if indistinguishability obfuscation exists. But I think the connections between the two things aren't really well understood yet. In particular, that result that by Pagliazzo and friends, it seems like there's kind of like a trick in it, and I don't know, it kind of seems like magic. So and maybe like too much like magic. Maybe there's something more substantial you could say there.
All right, thanks. All right, well, that seems like it might be all the questions. Nobody else has anything else. I guess we'll thank your speaker. Thank you, Rahul. It was a great talk. I really enjoyed it.
Thanks, I'm glad you enjoyed it.
Thanks, Rahul.
Maybe we should give a thanks to Magdalene and Isaac for organizing tea lunch in this difficult semester.